Okay, so we learned about the ladder operators. So we know about the ladder operators, and they are the raising operator A plus and the lowering operator A minus. We also learned how to obtain the state with the lowest energy, which we call ground state. How do we obtain this state? By applying the A minus, the lowering operator on this. So we know about the ladder operators. We know how to obtain this ground state. We also know the energy of this ground state. And from that, we said, now I can get any other state starting with this ground state. For example, if I want to get the first excited state, I just have to apply the A plus on this ground state. What does it mean to apply A plus? Well, we have to remember its definition. There are some constants here in front. Then there is minus IP plus m omega x. Well, remember that we are dealing with operators. No? So P here is an operator. Which operator? H bar over I dx. So we have to apply this whole thing on this function, this psi zero, which we know is a Gaussian function, and we are going to get the next state, the first excited state. However, when we go in this process, we have to guarantee, we have to ensure that this state, this new state psi 1 is normalized. So we have to check this constant. And you did this in example 2.4. There is also a video for this example 2.4. And in this case, it was we were very lucky. Now we found that this A1 is just 1. We solved integral of Gaussian functions, and we found that this is just 1. But in general, it's not 1. And it's a tedious procedure to obtain, to solve these integrals of Gaussians. There is another way to ensure normalization using the algebraic method. Very elegant, and that's what we are going to do now. Okay, so suppose we have a certain state psi n, and we want to find the next state, a higher in energy. What are we going to do? We have to apply the A plus. That's how we are going to get the psi n plus 1. But as we said, we have to ensure that this new state is normalized. I'm going to say that its normalization is some factor 1 over Cn. Okay, so what we want to find is what is this normalization factor. All right, this in the same with the same idea. If I have a state psi n and I want to get the state with lower energy, I can apply a minus, and we are going to get the psi n minus 1. But again, we have to ensure that it's normalized. So this normalization factor, I'll call it 1 over dn. So we want to find what is this normalization factor. Okay, very well. So let me rewrite these equations in this form. I'm saying here that A plus acting on psi n is some Cn that we are trying to find, psi n plus 1. Okay, so this is one equation. So our goal is to find what is the Cn. And the other equation that we have is A minus acting on psi n changes the function. It becomes dn of psi n minus 1. And we want to find what is this dn that ensures that this new state is normalized. To proceed with this, what we need to do now is we need to find a trick in this story, which is the following. Let me write the following integral. I have an integral of a function f, is a function that is normalized with a nice square integrable function, for example, of a psi. or solutions of Schrödinger equation, complex conjugate, and I'm going to put here A plus acting on another normalizable function G, okay, from minus infinity to infinity. And we want to show now, and this is going to be very useful to find those normalization constants. We want to show that this is equal to, I'm going to bring this A plus in front, and what we get now is A minus multiply, acting on that function, all that complex conjugate G dx. Okay, so this is what we want to show, and this is going to be very useful to find the those normalizing constants. How do we do that? Well, we have to remember what this A plus is. We wrote it above. So let me write what this A plus is. There is some constant that I'm going to put outside the integral. And then we have F. Now, the first term is this part that involving the momentum. But you see that the momentum has also an I here. So this I will cancel in the denominator and numerator, and there will be a minus sign surviving with this derivative. Okay, so that's what I'm going to put here. The only thing that survived was minus h bar ddx on G. But there is more to this A plus. We also have plus m omega x acting on G. Okay, so what I did here was just copying this A plus, but in terms of momentum operator and position operator. Okay, now I want to bring this whole operator, this A plus, to the front of this integral, as we did here. How can we do that? Now we have to remember how we do integration by parts, because look, what we have in this integral, one of the terms that we have in this integral is an integral of f, complex conjugate, derivative of g, dx, right? And we know that we can do this by parts and write it at f conjugate and g in the range of the integral, so minus infinity to infinity, and now minus, and I'm inverting the position of the derivative, and I put it here in front. Now I have the derivative of this complex conjugate of f, g. So this is a property that we already know. Well, we said that we are dealing with functions that are square integrable, so we know that they have to go to zero at plus infinity and minus infinity. So the only thing that survives is this term, and very important, with this minus sign. All right, so I'm going to rewrite the integral that we have above. So 2mh bar omega is there. Now I'm going to bring the derivative that we had here, acting on G. I'm going to bring it to the front, so it will be acting on F. And careful with what we said, this minus sign. This minus sign with this other minus sign becomes plus. And so we have here the derivative ddx of the complex conjugate of F. Now with the plus sign, we also have that H bar. Now, how about this other term? This other term is constants, no? M, omega, and x. All these functions, f and g, are functions of x. So I can move this x around with no problem. So I'm just going to put this x in front here, m omega x, also acting on this f function, g. Yeah? So I moved the derivative, correct? And now, what is it that I have acting on this function, f, complex conjugate of f? We can rewrite that in the following way. We have this constant, and now I can put h bar, this constant that we just wrote, h bar, m, omega, x, these are all real things. So I can put all these, including the derivative, inside the whole complex conjugate. So how I'm going to do that, I have h bar ddx plus m omega x, all that acting on this function, and I'm putting here this complex conjugate. Okay? I just copied what is above, because as I said, mass, omega, h bar, these are all real values. So it doesn't matter if I put it inside the complex conjugate or not. And what is this? What is this whole thing here? Is the A minus. Is the lowering operator, because the lowering operator is that constant that we see in front of everything. Then we have IP plus m omega x. So that's exactly what is written above, remembering that this operator is h bar over I ddx. So very good. We proved what we wanted. So this relationship, which is going to be very useful, has just been proven. The other relationship that you can prove on your own is equivalent to this one. I'm just going to write it, which is the following. If we had instead the function, and instead of having, remember here we had a plus. Well, if instead of a plus, I put here a minus g, the procedure is very similar, is again integration by parts, and we can show that this is equivalent to the integral, now a plus, acting on this function, everything inside of the complex conjugate, g dx. Okay, so I let for you to try to prove this. Okay, now, having these two relationships, let's continue. Remember, don't get lost. What we want to find, let's go up here. We want to find this Cn and this Tn. Okay, so I'm going to start from this side. I want to find this Cn. So let me rewrite this equation. What we want to find is, if we act with this raising operator on psi n, we get some constant Cn that will ensure that the psi n plus 1 is normalized. And we are trying to find what is this Cn. Okay, we also found that when I have A plus acting on G, we can rewrite this as A minus acting on F, like this. All right, let's see how this is going to help us. Okay. What we know we start from this assumption that this psi n is normalized. Okay, so this we know. And what we want to ensure that psi n plus 1 will also be normalized. So we want to find the Cn, we want to find the Cn that will guarantee that this is going to be ensured. How I'm going to start with this procedure? I'm going to start like this. I'm going to start by writing the A plus psi n conjugate A plus psi n. Okay, so I'm starting with this integral from minus infinity to infinity. And I'm going to see where I'm going to arrive with this. Okay, so this is my starting point. All right, so using this property here, we know that we can rewrite this integral in the following form. We can bring this a plus in front of everything, inside that complex conjugate, changing its sign. So we have here a minus a plus psi n, everything inside this complex conjugate, and psi n. All right, so now you see that we have a minus a plus, this combination of these two operators, acting on psi n. What is that? Well, let's think a little bit. We know that psi n is a solution of Schrödinger's equation, the time-independent equation. So we know that the Hamiltonian acting on this psi n is energy of that state, psi n. Very good. What is this energy? We found this is equation 2.62 in a book. We found that this is h bar omega n plus half. Okay, so this is something that we already know. And we found ways of writing this Hamiltonian operator in terms of the ladder operator, in terms of a minus and a plus. And so one way to do that is like this. A minus, a plus, minus half psi n. Yeah? So this is an equation from your book, and this is the equation 2.54. Okay, all right, so if I look at this equation, let's see. I can cancel this h bar omega, and I find that a minus a plus acting on psi n, which is what we have here, plus half on psi n is equal to n psi n plus half psi n. Okay? So if we rearrange what we just wrote here, you see that a minus a plus acting on psi n gives us n plus 1. No? Sorry, here I wrote a wrong sign. This is still minus, just as we have here minus, this is minus. When I pass to the right side, that's when it becomes positive, and that's when I get this plus 1. So this is what we are going to use above. All right. So our the right side of this equation becomes now, and I can remove this whole thing to give us. So this right side now becomes n plus 1 is a constant, so I'm going to put it outside the integral, n plus 1. And then what survived inside the integral? Psi n complex conjugate psi n dx. And we know that this function is normalized. We started from this assumption that we had already normalized this psi n. So we know that what we get here is just n plus 1. Okay? So this is the right side. Very good. Now, how are we going to proceed with the left side? So how are we going to proceed with this part here? Well, we started by writing the equation like that. Now we are trying to find this Cn. So I'm just going to rewrite this. Okay, look carefully. I'm going to rewrite this on the left side. So what do we get? We have inside this integral a plus act on psi n gives us Cn psi n plus 1. Okay, so I'm putting here Cn psi n plus 1, but all that in the complex conjugate. And the next one, Cn psi n plus 1. Okay, so what is this? Well, Cn is just a constant, no? It's associated with the normalization that we are trying to find. So let me get this out. So this left side is going to be Cn absolute value square, because here we have Cn complex conjugate and Cn, so absolute value square of Cn. What survives inside is this psi n plus 1, complex conjugate psi n plus 1 dx. We said we want this to be normalized. We want to find the Cn that guarantees that this integral is normalized. So putting things together now, we find that this Cn absolute value square has to be equal to n plus 1. This will ensure normalization. So then we found that Cn is the square root of n plus 1. And so our equation a plus of psi n gives us square root of n plus 1 psi n plus 1. Okay, so this is how we get the new function, the function psi n plus 1 normalized. Starting from a function that was already normalized, we know that psi n plus 1 is normalized via this factor, square root of n plus 1. Okay, so this is a very important equation. Now, how about the other one? The other side, we said that a minus action psi n should give us something that we are trying to find, some gn that we are trying to find, psi n minus 1. So following the same procedure that we did above, we can obtain this dn. I'm going to already put the answer. This dn is square root of n. Let's try to show this. Okay, so starting again from very similar relationship, but now before we started with a plus psi n, a plus psi n, and everything followed from here. Now you have to start from a minus and follow the same procedure. What we are going to do, first step, bring it in front of everything, and now we have a plus, a minus, psi n, and this psi n. Again, if we remember that this psi n is a solution of Schrödinger's equation, we know that the Hamiltonian acting on psi n gives us energy, psi n. A way to write the Hamiltonian is h bar omega, a plus, a minus, plus half, equals to the energy, which you also already found, which is this equation. From here, similar to what we did above, you realize that a plus, a minus, this combination of operators acting on psi n, gives us n psi n. This is very important, okay, to realize this. No? Of course, it came from Schrödinger's equation, but this is a very important relationship that we can now use above. So let me get space as we did before. We can use this here and say that what we get is this n. So I'm going to put it outside the integral. Psi n conjugate multiplied by psi n. This is absolute value square of psi n. Due to normalization, we know that this is 1, and the only thing that survives is 0. Very good. On the left side now, as we had done before, we are now going to substitute this by dn on psi n plus 1. Oh, sorry, if it's lowering, of course, it has to be minus. And the other one, dn psi n minus 1. Okay, so what we get from here is this dn is a constant, so I'm putting outside the integral, and here what survives is psi n minus 1. We want it, again, we repeat, we want this to be 1, and we want it to be normalized. So conclusion, to have normalization, we get that dn has to be square root of n. So what I got here is this side equal to that. So that's what we wanted to show. Very good. So now let's put these equations together. What we found, and this is very important to know, this derivation. There are many important things that we did along these derivations. But what we found, a plus on psi n is n square root of n plus 1 of psi n plus 1. Very important, very good. This makes life easier once we know this relationship, as we said. Now we get the normalization in a much easier way than solving integrals of Gaussian function. And a minus of psi n give us square root of n of this new function n minus 1. All right, very good. So you see now, if we have the ground state, we can get any other state, as we already said. So if I want to get psi 1, what I'm going to do, a plus action psi 0, right? And if I look at this equation here, divided by square root of 1. It's silly to write it like this, but let's keep it this way. So what I did to write this equation is I just wrote what you see on top here. I wrote it like this. Psi n plus 1 is a plus action psi n divided by square root of n plus 1. So I got my psi 1. And you see that we got here square root of 1, which is just number 1, which is what you found in the example 2.4, but much more complicated way, solving the Gaussian integral. Okay, but let's continue. If I now want to get psi 2, what we are going to do, we are going to act with a plus on psi 1, and following this equation, I'm going to put here square root of 2. Well, but using what I have from above, I see that this is a plus on the ground state. And here we have square root of 2, square root of 1. Let's continue because I want to show where we are heading towards. Psi 3, I apply a plus on psi 2. And following that equation, the general equation that we have, I divide this by square root of 3. Well, using what we have above, we see that this is a plus 3 times. Square root of 3, square root of 2, square root of 1, and ground state. So you see that if you go in general, you will see that any state psi n is just a plus n times applied on the ground state. And here in the denominator, we have n minus 1, n minus 2, n minus 2, 5, 4, 3, 2, 1, all this in a square root. In other words, psi n is a plus acting n, a plus acting on the ground state, and the normalization factor is square root of the factorial of n. Okay, so that's our general expression already normalized. So that's the end of this video.